All right, what's up, guys? In this video, we're gonna pick up with some calculus here. It's gonna be another integration practice video. It's gonna be another improper integral, but it's gonna be example number 60 of the integration practice series. All right, so we're asked to evaluate the improper integral or state that it diverges. So we got this improper integral from 1 to infinity. We got ln of x over x squared dx. So again, what an improper integral is basically a specific type of definite integral, and there's different types of improper integrals, but where either you have infinity or negative infinity in some cases as either one or both of the limits of integration. An integral can also be considered improper if it has a discontinuous integrand on the interval of integration. So those are a little harder to spot, but that's what an improper integral is. There's various types, and we've done plenty of examples on how to deal with these. So since infinity is not a finite value, you can't just blindly apply the fundamental theorem of calculus and say, well, I'm just going to plug infinity in because infinity is not an actual number. It's not a finite value. So what you have to do is you have to replace infinity with a variable, typically t, and then take the limit as t goes to, in this particular case, infinity, or if it's negative infinity, as t goes to negative infinity, depending on the example. So I've done plenty of examples like this. So we'll take our integral, which is the improper integral from 1 to infinity. We got ln of x over x squared dx. So now this just becomes the limit as t goes to infinity, and I'll take my infinity here and replace it with t, and now we got ln of x over x squared and then dx. So that's how you set it up. Now sometimes the integrals are easy to compute off the top of your head and you know the antiderivative immediately, and in that case, well, you just plug in from 1 to t and then take the limit as t goes to infinity. But if you don't know the antiderivative off the top of your head, you really approach it no different than you would any other integral and just compute the indefinite integral first and then come back. So I know what the integral of ln of x squared is. I'm going to have to use integration by parts. I have a general idea. But let's go ahead and compute the indefinite integral first. So again, to evaluate this, and we've done plenty of examples, we apply integration by parts. Remember, that's the integral of u dv is equal to uv minus the integral of v du. We need a u and a dv. So obviously the best selection for u is ln of x, because if we let dv equal ln of x, well, then that means that to get v, we would have to integrate dv. And integrating ln of x requires integration by parts. It's not hard, but it's a little bit more work than we need to do. And obviously, if we let dv equal that anyway, we need to know the answer ahead of time, at least for the ln of x portion. So obviously, that's not the best selection for dv. And ln of x is a whole heck of a lot easier to differentiate than integrate. So we know the derivative of ln of x is 1 over x. Don't forget to multiply by dx. And then we integrate 1 over x squared dx, which we know is negative 1 over x. Now, remember that when you're doing your selection here for integration by parts, it's important that you let dv, after you've pick u to be ln of x, it's important that you let dv be 1 over x squared dx. You can't just put x squared, because we have, you could think of it as being a 1 on top, just an x squared at the bottom. So students will make that mistake, especially with problems like this. They'll do the right selection for u, choose that to be ln of x. Then they'll pick dv to be x squared, but x squared here is in the denominator. So you can imagine there's a 1 on top. So you can't just pick dv to be x squared. So just keep that in mind. So now when we do integration by parts, I'm going to go ahead and kind of clean it up together. I'm bringing the negative to the side over here. So we'll have negative ln of x all over x. Two negative signs will make a plus. So then we'll have the integral of, again, 1 over x squared dx after we apply the integration by parts formula. Now, again, we know that the antiderivative of 1 over x squared dx is negative 1 over x. We know that already. You did that on top there. So that basically once we have done the second integral on the inside here for integration by parts, we'll end up with negative ln of x over x minus 1 over x. Or actually, we would actually be done with the integration by parts. It would be negative ln of x over x minus 1 over x plus c. If we were actually doing this as just as a general indefinite integral, let's say we were just doing it and it wasn't a let me adjust the screen here, just the lighting, I don't want to be too bright. If we're just evaluating the indefinite integral just in general, this would be your solution to the integral of ln of x over x squared. But in this case, the improper integral. So we're just going to take our antiderivative, and now we're going to take the limit as t goes to infinity, and we got to plug in from 1 to t. So the integral that we started with was from 1 to infinity, and it was ln of x over x squared dx. And what we did was we write it as the limit as t goes to infinity. We replace the infinity there with a t. This is ln of x over x squared. We compute the antiderivative already. We did that. So we get the limit as t goes to infinity. And we take our antiderivative, which was negative ln of x over x minus 1 over x. But it's going to be from 1 to t. So hopefully you with me so far on all that. So now we use part 2 of the fundamental theorem of calculus. So we get the limit as t goes to infinity. The t goes first, so that'd be negative ln of t all over t minus 1 over t minus, and then you plug in the 1. So be careful with the signs here. Now if we sub in a 1, keep in mind there's a negative there, so it's important to use parentheses here. So this would be negative ln, and we'll do the simplification in a minute, but I'm just writing everything down for right now. So we'll have negative ln of 1 all over 1 minus 1 over 1. And now we clean it up. So we get the limit as t goes to infinity. And when we clean this up, we get negative ln of t all over t minus 1 over t. Remember, ln of 1 is 0, and 1 divided by 1 is obviously just 1, but there's 2 negatives there, so this will become a plus 1. So you have to be very, very careful there with the sign changes. And now we just take the limit as t goes to infinity for negative ln of t minus 1 over t plus 1, and that's obviously just 1, where we get a finite value. So clearly this improper integral converges because the limit exists and we get a finite value, which is 1. So your final answer here, the integral from 1 to infinity, it's an improper integral from it's going to be ln of x over x squared dx. Again, it obviously converges because the limit exists and we get 1. And that's your answer. All right. So that's just going to be added to the number of videos that we have done so far with improper integrals. Alright, so if you guys got any questions about this, let me know. Hopefully the explanation that I provided you for this was pretty straightforward. But let me know if you have any questions, and I will see you guys next time.